quantum optics. And it gives me enormous happiness and pride to say that quantum optics, if you ask, the first PhD probably was in quantum optics was that of Professor Anantha Lakshmi with Professor Girish Agarwal. And you might have heard, we were talking about him. He's sort of the inspiration behind us all. In Hyderabad, we started this school, which really brought, quantum optics to India. I would say earlier it was optics, but hardcore quantum optics in conjunction with experiment. Of course, many schools are there in different aspects, non-classical nature applied, function, theory. But he's the person who brought it to the extent of, really hand to hand with experiment. For example, Professor Anantha Lakshmi's thesis, if I remember correctly, was an optical Hanley effect, which led to Professor Agarwal's Bhatnagar Award later on. And since then, she has been one of the, pillars of quantum optics in India. I actually sort of saw the power of quantum optics when I collaborated with her a few years back, because it is special in the sense that when you do, light is always subtle. As you might have heard, Professor Ajay Ghote was mentioning about Einstein telling these days every fool thinks he knows of the photons, but I'm still wondering about it. So that's the reason, since the running theme is optics, we specifically requested Professor Anantha Lakshmi to start, the very basics about, what is photon, how do you quantize it, and since, and then subsequently all these non-classical states. So I request Professor Anantha Lakshmi, please go ahead.
Thank you, Prashanta, for a generous introduction. And I hope the recording has begun. Let us start. Okay, so today I'm just going to be giving you lecture zero lecture in 101 quantum optics. So as the name quantum optics suggests, you are looking at the optical phenomena at the quantum mechanical level. Namely, if you are looking at what is popularly, everybody says light matter interaction. So when you look at the light matter interaction at the level of, just a few quanta of radiation interacting with just a few material particles, like a few atoms or, whatever, then you necessarily have to look at this interaction at quantum mechanical level, which means you have to treat light as a quantum mechanical entity as well as matter as quantum mechanical entity. Matter as quantam mechanical entity, Schrodinger equation and all these things, they have done all the work for us. And what we do here essentially is, how to quantize the radiation field, because quantization of the radiation field is very basic to understanding any of the quantum optical phenomena which you would come across in your subsequent lectures, or in, when you open a quantum, when you, look at the high-end experiments that are happening these days. Okay, so we have to begin our discussion with the quantization of the radiation field, because, when we were doing our second year or third year electromagnetic theory, we were taught that Maxwell's equations describe the, electric and magnetic fields, the dynamical evolution of the electric and magnetic fields, both in space and time. So what we do here also is to start with the classical electromagnetic, the propagation of electric and magnetic fields through the Maxwell's equations, and down the line we just add a little bit of information and certain other ingredients, inputs into that, in order for it to be suitable for our use in the quantum optical interactions which one treats. Okay, now I cannot do justice to quantization of the radiation field in one lecture. So what I will do is I will quickly mention the basic steps that are involved here. So as a first step, what we do is we consider a plane electromagnetic wave which has got frequency, let us call it omega k, and it is propagating in the direction k. So let us write down the electric and magnetic field vectors. First step is to quantization of the radiation field. Okay. Yeah. Oh, am I not sharing my screen? I removed your sir. Okay. Okay. Quantization of the radiation field. Basically, we write the electric and magnetic field, the plane wave expression. You probably are aware, but just for the sake of, some kind of continuity here, we will just write it I k dot r minus I omega kt. Omega kt is the frequency of the electric field, and the magnetic field is simply k cross p by k modulus the amplitude of that E naught e to the power of I k dot r minus omega k t plus complex conjugate. Here, this k is simply the modulus of the wave vector, which is your omega k by c. C is the velocity of light, of course. And the epsilon which you are writing here is the polarization vector for the electromagnetic field. So this is your expression for the electric and magnetic fields. And now what we do is, from this, we already have all the information from Maxwell's equations. So from that, we quickly write down the energy of the electromagnetic field, which is contained in a volume V, which we again get from Maxwell's equation. So the electromagnetic, the energy of the EM field in certain volume, in a volume V, you can write this from Maxwell's theory. So this usually the notation which is used is U. This is equal to 1 by 8 pi. You have integrated over the entire volume your E square R comma T plus B square R comma T integrated over the volume. So this is your energy, the energy content of the electromagnetic field. And for a plane wave, it simplifies further, but okay, so let me just write down that also anyway. So for your plane wave, which we have already written down the expression for above, for a plane wave, this becomes 1 by 2 pi E naught square V. So this is the expression. Now, after this, what one does is that, it happens that it is convenient to work with what are known as the vector and scalar potentials when you are dealing with the radiation field. So we use we write this electric field and magnetic field in terms of the vector potential. And after that, what we do is we work in the Coulomb gauge and we set up the equation for this. And what you realize is that here, basically, as I have already mentioned, you are considering the electromagnetic field which is confined in a box, which you this box quantization. You take the box to be of length L and volume V, and you expand the field into a complete set of plane waves after you have transformed the electric and magnetic fields, after you have re-expressed them in terms of the vector potential. So this complete set you obtain and you impose the periodic boundary conditions on the walls of the box. And after that, you obtain an expression for your, after you have re-expressed your electric and magnetic field in terms of the vector potential, the emerging expression for the vector potential has the form something like this, A R comma T, which is the vector potential. This is all, Jackson stuff. Okay. You are all familiar with this, but we are just touching upon this in the context of the quantization of the radiation field. So this is Ks divided by volume V epsilon Ks e to the power of I k dot r minus omega t plus complex conjugate. So this summation here is carried over the load values of the wave vector k and also the S, which are the two polarizations for each K that are allowed because of the nature of the transverse nature of the electromagnetic field. Okay, now after you make the gauge Coulomb gauge, you use the Coulomb gauge because you are basically dealing with the non-relativistic situation here when you are working in quantum optics. After you have done all some certain a few number of steps down the line, finally the expression which you obtain for the energy has in terms of the energy in terms of electric and magnetic fields we have already written down, but the energy in terms of vector potential comes out to be something like this. So this looks something like this. U is equal to 1 by 2 pi sum over Ks. K is basically this omega K square by C square A Ks mod square. And here we have already expressed this omega K is equal to Ck. So now the energy of the electromagnetic field is expressed as a sum over the modes, and each mode is a plane wave with a certain polarization, which you have written the expression for earlier. Okay, now with this, now the stage is set to proceed with the quantization of the radiation field. Now this U, we can sort of rewrite this something like this. So we can write this U as U is equal to sum over, re-expressing this as H bar omega K NKS. Once you do this, you can obtain what is the NKS in this. So this, with this substitution, the expression for NKS comes out as, you have multiplied and divided by H bar so that you can pull out one H bar omega K term. So this gives you 2 pi H bar C square times AKS modulus square. So this is your connection between this is the expression, and from this you get your NKS to be given by this. Now, so this is the energy content of the electromagnetic field in a volume V, which we have considered. Now, what we do in quantum theory? In quantum theory, all the fields, like, what are the field, what are the quantities that are representing the fields for us? Electric field E, magnetic field B, and the vector potential A. So these things, they are expressed, they become operators in the when you graduate to quantum mechanics. So in quantum theory, let me use a different color. In quantum theory, all the field variables become operators. Okay. And the energy, because all these things become variables, become operators, we know the correspondence between the energy. What is the energy operator? U becomes the Hamiltonian. Okay. Right. So this is the connection between the radiation field, and now because NKS contains this AKS modulus square, and the operator correspondence between this AKS and the corresponding quantum mechanical operator is written something like this. This AKS, its operator avatar is AKS, and AKS star goes to AKS dagger. So these are the operators. So these are the quantum mechanical operators. So in terms of this, and also I have absorbed the other stuff into this, writing this AKS there, so that your NKS becomes something like this. This NKS becomes A dagger KS AKS. And these operators, interestingly, they obey the commutation relations given by, the commutation relations are given by A dagger. This is delta K prime S prime, let us write. So K prime delta S prime. So this is the commutation relation, and also any operator commutes with itself, so that your A Ks, the commutation relation between A Ks and A K prime S prime is simply 0. Now there is this observation that these operators A and A dagger do not commute with each other has an interesting consequence. What is that? This A dagger do not commute with each other, and this is because all the field operators, like electric field, magnetic field, and the vector potential, these are all linear. They are expressible linearly in terms of this A and A dagger. Whereas if you look at the energy is quadratic in A and A dagger. So even if the operator's expectation values are 0, the energy can still be non-zero. That is the consequence of this non-commutativity of these operators A and A dagger. And now, I have very little time. If you want, I will send you a detailed notes on this, but we will move on to something more interesting than this. Now, the energy which we have upgraded to the Hamiltonian operator H has the form H becomes the Hamiltonian H takes the form sum over the modes Ks half H bar omega K times A dagger Ks plus A dagger A, sorry, A dagger Ks AKS plus AKS A dagger Ks. So this is what you obtain by making the substitution, and this by virtue of the commutation relation, this becomes sum over Ks H bar omega K N Ks plus half, where your NKS is given by this. Okay, so this is what is the expression. Now, if you look at this expression, you will immediately realize that this is something which you have come across in your 101 quantum mechanics course, which is nothing but the energy operator for the harmonic oscillator. Okay, now here, as we said, there is an interesting consequence of this A and A dagger not commuting with each other. Namely, even when there are no, even when this NKS is 0, that means even when there are no photons in the field, there is still some non-zero energy which is given by H bar omega K by 2. So this is referred to as the 0-point energy of the electromagnetic field. So here, this sum over Ks H bar omega K times the half. So this is referred to as the 0-point energy of the field. Okay, now the next point which I would like to bring about quickly is that in quantum theory, we write any Hermitian operator. This is a basic quantum mechanics. In quantum theory, you write all Hermitian operators. Let us talk about this in the context of the radiation fields. So we will mention Hermitian field operators. So these, let us denote them by some general symbol F, which could be any of these things. It could be A, it could be E, it could be B. Okay, so this in quantum theory, it becomes advantageous to write these things as something like this. So this F, which is a function of position variable and the time, is expressed as something called a positive F plus R comma T plus F minus R comma T. So this representation is referred to as the analytical signal representation. And here, F minus, the connection between F minus and F plus is that F minus is the adjoint of F plus, and this F plus contains only positive frequencies. So this F plus contains only positive frequencies, and F minus contains the negative frequencies. And so because this contains only the positive frequencies, you can immediately see that F plus contains only the annihilation operator. Okay, so this contains only the annihilation operators, whereas F minus contains, I'm putting plus and my, okay, so I have to put a bracket here also. F minus contains the A dagger Ks kind of operators, which contains the creation operators. Okay, so I jumped into annihilation and creation operators. We have expressed the harmonic, we have expressed the energy of the energy content of the electromagnetic field in a volume in terms of this vector potential, and we have identified that as h bar omega chi nk. Then we obtained an expression. Then by making the identification, we obtained an equivalent expression for this nk. And when we are looking at the radiation fields, what are we looking at? We are looking at the radiation field interacting with matter, which is referred to as your light matter interaction. And here, what can happen with the radiation field? The action between the interaction between the radiation field and the matter can happen in two ways. Either it is basically energy exchange. So the energy exchange can happen in two ways. The atom can give energy. If an atom is already sitting in its excited state, then atom can give energy to the radiation field. Or if the atom is in a ground state, then the radiation field can give energy to the atom so that the atom goes into the excited state by absorbing this energy. So the two processes that can happen here are absorption and emission of radiation. So when you are looking at absorption or emission of radiation, and when you are looking at radiation, as I mentioned at the beginning of the lecture, that in quantum optics, you are dealing with few material particles interacting with few quanta of radiation. It is instructive to, deal with the radiation field in terms of this creation and annihilation operators, because what is happening to the radiation field is that it is either the difference between its initial state and the final state is that it has either lost some quanta of energy or it has either gained some quanta of energy. So that is the reason, that is the purpose, that is the reason because of which we are developing the theory. It is convenient to develop the theory in terms of this creation and annihilation operators and the commutation relation. So all you need to know is that these operators A and A dagger do not commute with each other. Their commutation relation you need to know, and the energy A dagger A, what is the expression for energy A dagger A. Knowing these things, you can develop the entire algebra related to this. Okay, now and also I brought in this extra other point that in when you are dealing with the quantum theory of radiation fields, you represent the field operators, which are the Hermitian operators, in terms of you write it something like this: F RT is F plus RT plus F minus RT, and this F plus and this is the positive frequency part. F plus RT is the positive frequency part, and F minus RT is the negative frequency part. So F plus RT contains AKS and F minus RT contains terms like A dagger Ks. And also this decomposition has a it is got a significance, namely that this decomposition is related to how the photon detectors respond to the electromagnetic field. Now we have when we are looking at the radiation field in free space as a final step, what we would do is we take the limit v going to infinity at the end of the calculation. That means after you have calculated all the physically measurable, observable quantities, then you take the limit v going to infinity. So that is how all this is done. Now, the next step is, we have now identified the, we have now quantized the radiation field. So after you have quantized the radiation field, in quantum theory, what do we know? We know that all observables are represented by Hermitian operators, which you have already mentioned, and also the expectation values of these Hermitian operators in the state of the quantum system will give us the measurable quantities. Now that means we have to now worry about the state of the radiation field. So we need to find ways of identifying the state of the radiation field. So which is what we will do now. So this initially we Bose, Einstein, this quantum theory or quantization radiation field is due to the efforts of many people. Like it started with Planck, Dirac, Bose, all these people have made significant contributions. I have missed out many names. Wigner also has participated in this exercise. So what down the line, Einstein I forgot, which is, okay, fine. So quantization of bosons with the finite mass, which was done, it was done initially by Fock, and the state space of this is referred to as the Fock space, and the states are called as Fock states. So our electric field, all the field operators as written as the superposition of all the independent modes. What we can do is we can construct the states for each mode, and then we can, because these modes are independent, we can upgrade the single mode analysis to multi-mode in a straightforward manner. Now, what we need to do is we need to construct the state space of a single mode. So the next step is we have to construct the state space for a single mode field. And the operators which are representing the field are our, because it is single mode, we will dispense with, we will forget we will not mention Ks because we are dealing with single mode. So Ks, we just not worry about it. So let us come back to our single mode. We have A and A dagger are the operators with the commutation relation A dagger is equal to 1. So this after the algebra, okay, so after algebra you get the states corresponding to the single mode radiation field. They come out to be, which you have done in your quantum mechanics 1, namely the harmonic oscillator eigenstates in the algebra of A and A dagger. So you have your A dagger A acting on N is N on N. So these are the states which are the eigenstates of the this eigenstates of the operator A dagger A, which is proportional to energy of the radiation field, and the states are known as number states because the eigenvalues are numbers, positive numbers, 0, 1, 2, 3, etc. So this N takes the value N is equal to 0, 1, 2, etc. So these N states, because they were developed by Fock, they are called Fock states, and also because they happen to be the eigenstates of the number operator, they also are called as number states. Okay, and because this N starts from 0, there is a lower bound on these states. So the lower bound is, and what is the connection between what are these operators? We denoted this. We have, when we brought in these operators A and A dagger, we said that this operator A works, operator A acting on the state of the system. Operator A, we call it as annihilation operator, and A dagger as the creation operator, for the simple reason that, when you develop the algebra, you will find that A acting on N takes it a state n-1 with the multiplying number root n. Similarly, A dagger acting on a given state takes it to a state n+1. So because of this, in the harmonic oscillator context, you call them as ladder states, and in the radiation field context, you call them as creation and annihilation operator. So if you write down the ladder of states, they look something like this. They are interesting feature here is that the difference between energy difference between each of these states is equal. So you are going to go from a lower state to a higher state by the action of A dagger, and similarly you can go from a higher state to a lower state by the action of the operator A. So this is how it works. Okay, so this is the state space. After we have quantized radiation field and done all this, this is the state space in which describes a field with definite number of photons in each mode. Okay, and this zero, okay, so because this is bound, this has got a lower bound, we this is n is equal to 0, corresponding state is 0, corresponding state is 1, 2, etc. So this is what we are writing is this is n. Okay, so what else do we know? The lower state, the lowest state being 0 and A being identified as the destroyer of the quanta, there is no more destruction possible. So this is the lowermost state. So because the 0, the lowest state, is referred to as the vacuum state, and it does not, vacuum means there is no quanta. So this contains no quanta of the radiation field. Okay, now this description of the state is useful when you are looking at field with a definite number of photons. Okay, before that, we will also define what shall we define? We will define the quadratures of the radiation. Okay, let us not do that right away. So this, we have quantized radiation field and we have obtained the energy expression in terms of the field operators. And now we have also argued that in quantum mechanics, field operators are expressed in terms of Hermitian operators, and their average values are, their measurable average values are obtained by writing by calculating the expectation values in the state of the radiation field. So we saw the necessity to describe the state of the radiation field. So this state which we have so far discussed is known as number state or Fock state, and it has got the limitation that it can only describe field with definite number of photons. Now, when you try to calculate, okay, so A and A dagger, these describe the field modes. Now, if we look at the expression, let us write down A n. We have to write the expectation value, right? So A n n. So this is root n times n minus 1. And usually in quantum mechanics, you always have done this whenever you have done the solution of a given quantum mechanical exactly solvable system. You have seen that you are always writing the states as orthonormal states. So here also same thing works. These n and n minus 1 are the states corresponding to different independent modes. Because of that, they are orthogonal to each other. So this is 0 when n, because n is not equal to n minus 1, which means whenever you calculate n, A dagger, n, all this is 0. So our field, average field, which is expressed in terms of a linear combination of A and A dagger. So this electric field, when you try to calculate the expectation value, it is coming out to be 0 in the state n. Okay, now in classical theory, at the classical level, what do we know? We know that we can, classically, we can have a well-defined electromagnetic field. So let us mention that. So classically, we can have what is well-defined electromagnetic field, which means field which has got and what is the field represented as? The field is represented as some E0 at the classical level. So E0 with well-defined amplitude and phase. Okay, right. Now, what did we do? We replaced when we were going through the steps of quantization of the radiation field, this E naught got replaced by the operator A, and E naught star became A dagger. Okay, so now, and what did we see? So when we go from the classical description of the radiation field to the corresponding quantum mechanical description in the notion of the quantized radiation fields, the average value of E naught, so we would identify this E naught would be identified with the expectation value of this A and A dagger. So E naught would be related to expectation value of the operators of A. And also this is an operator we should strictly have had, but due to paucity of time, I have not been doing all these things. Okay, but now for Fock state, what did you find? For Fock state, we found that this for Fock state, this A expectation value has turned out to be 0, which means Fock state does not represent fields with well-defined amplitude and phase at a classical level. So this is an important point. So we will mention it. So the Fock state is not capable of, so for Fock state or Fock states, we'll put it, why only one state? Fock states do not represent fields with well-defined amplitude and phase. This is the limitation. And phase. Okay, and more importantly, at the classical level. So this is the limitation the Fock state imposes on this. So having defined this, before we move on to finding states which are appropriate in describing the electric field with well-defined amplitude and phase, let me introduce to you just a couple more notations which are very frequently used in quantized radiation fields in quantum optics. So we define in quantum optics what are known as the quadratures of the radiation field. Sorry, I'm jumping from one to the other, but I promise you, as I have seen some requests, I will send you a detailed notes to compensate for this jump here. Quadratures of radiation field. So you write your A and A dagger are the complex operators here. If you look at the expression, if you look at the electric field expression at the classical level and look at the corresponding quantum mechanical expression, you will see that A case and A dagger case, they are complex operators. So this A quadrature of the radiation field, A plus A dagger by √2. Let us call it as X, and Y A minus A dagger by √2i. So our A and A dagger are not Hermitian. However, A dagger A is Hermitian. So from these non-Hermitian operators, we are trying to construct two Hermitian operators so that by calculating the expectation values of this, we will obtain the measurable quantities about the radiation field. So this X and Y is X is equal to A plus A dagger by √2, Y is A minus A dagger by √2i. So these are referred to as the two quadratures of the radiation field. So these are referred to as this X and Y are referred to as the quadratures of the radiation field. And if you map it to the definition, if you map it to the information that the electric field amplitude is a complex quantity, you will immediately be able to find the information that X relates to the amplitude, the real part of the amplitude, and Y relates to the phase of the radiation field. Okay, so these are the two quadratures of the radiation field. And now when you go back to your number state and calculate the quadratures, what did we find? In the number state, in the Fock state or number state, we had this limitation N A N is 0, and similarly because n an is 0 means n a dagger n also is 0, and as a result n x n is 0 and n y n is also 0. N y n also is 0. That means the field operators and the quadratures, all of them have 0 value in the Fock state, Fock state. So however, we have argued that here we have mentioned, we have brought in the information that at the classical level, a well-defined electromagnetic field exists. We talk about well-defined electromagnetic fields. When we say well-defined, we mean with well-defined amplitude and phase, which means we have to ask the question now. We now ask the question, what is a state which of the radiation field which can describe a field with well-defined amplitude and phase at the classical level? So the question which we ask now is, what is the state that can describe the radiation field with well-defined amplitude and phase at the classical level? Okay, so we do know independently that the field produced by a single mode laser is coherent. And what do you mean by coherent? It has got a well-defined amplitude and phase. Therefore, what is the appropriate state that can describe the laser field? The field coming from a single mode laser. That is the question. We modify the question to address the issue. So we are looking for the state of the radiation field that can describe the field coming from a laser. Okay, which means we are looking for a solution to the eigenvalue equation. We are looking for a solution to the eigenvalue equation. A and alpha is equal to alpha and alpha, and we require alpha to be normalizable. Then we have a solution. Okay, so what we are doing here is that we have realized that the Fock state is not capable of describing fields with definite amplitude and phase, with a well-defined amplitude and phase, because the average values of the field operators are all becoming 0 in the Fock state. So we ask the question, classically we are aware that the field, there exists field with well-defined amplitude and phase, which means when you calculate these quantities which I have introduced here, the quadratures x and y, which correspond to the amplitude and phase of the radiation field, should have non-zero expectation values in the state which describes the field with well-defined amplitude and phase, which means we have asked, and also we also have information that laser field, the field coming from a single mode laser is coherent in nature, which means coherent, what do you mean? Where there is a well-defined amplitude and phase. Whatever is the extent over which it remains coherent is an independent question altogether, but it is coherent in nature. So we ask the question, what is the, if we can find a solution to the eigenvalue equation, A on alpha is equal to alpha on alpha. So this alpha is a complex amplitude. So this alpha is a complex amplitude. So this alpha is complex amplitude. So if we find a solution to this eigenvalue equation, then our problem is solved. It indeed is found, and this work was done by Glauber, and he received a Nobel Prize for this and other contributions he made to the field of quantum optics. In 2005, he received the Nobel Prize, and he proposed this coherent states in 1963. Okay, so this Glauber has found a solution to this problem, and later on, and also parallelly, Sudarshan also has done extensive work on these coherent states. However, Glauber got more recognition for this, and so let us not dwell on that. So this A alpha and alpha and alpha. So this alpha, because they describe the laser single mode radiation field coming from a laser, they are referred to as coherent states. So these alpha are called as coherent states, and they are normalizable so that you can make measurements in this. Okay, now this alpha, since our number states are complete, they form a complete set. This alpha, you write it sigma n is equal to 0 to infinity Cn n. So after you do the algebra, you find that this alpha comes out e to the power of alpha square by 2 sum over n alpha to the power of n by square root of n factorial n. So this is the coherent state, which is expressed in terms of number states. Okay, so this it will take me 5-10 minutes to do the intermediate steps. Since I do not have time, I'm not doing this. So why all these states? In quantum optics and in this 101 quantum optics course, you are basically interested in, you know, the precision measurements. So how do we bring in precision here? By looking at the uncertainty relation. So your x and y quadratures, which we have written down here, x, y, x is, we have already written down x is equal to a plus a dagger by root 2 and y is a minus a dagger by root 2i. So if you write the commutator of x and y, it will come out to be, what will it come out to be? 1 by root 2, 1 by root 2 will become 1 by 2i, a plus a dagger, commutator with a minus a dagger. So this, after you do the simplification, you know a commutes with itself and a dagger commutes with itself. The non-zero contributions are coming from 1 by 2i, a with a dagger with a minus sign, and that is 2 times. So minus 2. A with a dagger, you know that a dagger is equal to minus of a dagger a, basic. So this is gone into writing this expression. So 2 goes away and you get a minus a with a dagger. Okay, fine. So finally you get x comma y comes out to be I or minus I, doesn't matter. Then your uncertainty relation, you know how to do that, right? So if you have any two operators, a comma b, if they do not commute with each other and their commutator is given by this, then general uncertainty relation you write down from here as the general uncertainty relation comes out as delta A, delta B is greater than or equal to half modulus of C. So this is a general uncertainty relation. So for our x and y, your delta x, delta y is greater than or equal to half. So this is the uncertainty relation between the two quadratures x and y. So delta x, delta y is greater than or equal to half means what is the minimum value possible? The minimum value possible for the product is, delta x, delta y can be half. So when you calculate this product delta x, delta y for the number state and do it for delta x, delta y for the number state, you will get it to be equal to n plus half. Delta x, delta y is iso, h bar will not be there, n plus half. Whereas for the coherent state, your delta x, delta y for the coherent state is always equal to half. So this means that this implies that only n is equal to 0 is a minimum uncertainty state. The ground state is a minimum uncertainty of the oscillator is a minimum uncertainty state. We know this already. And delta x, delta y in a coherent state is equal to alpha. And what did we say what this alpha is? This alpha is a complex number. Alpha is the amplitude of the field, and it is a complex amplitude of the field. It's a alpha is the complex amplitude of the field. So what do you find in a coherent state? The interesting result is that this uncertainty product between the two quadratures delta x, delta y is always equal to its minimum value regardless of what is the amplitude. It does not depend on the complex amplitude of the radiation field. It is equal to half regardless of what is the complex amplitude of the field, which means as which has got an interesting consequence. Sorry, I'm not able to get into that. So this tells us that, so from this we can write it as coherent state is a minimum uncertainty state. And what is so interesting about minimum uncertainty states, when you look at this cup is half full or half empty. So we look at half full situation. So if it is a minimum uncertainty, means maximum precision possible. Minimum uncertainty implies maximum precision possible, which means when you are using a coherent state to make measurements of these observables, you are going to be able to obtain maximum precision possible. Same thing, maximum precision possible is only for the ground state of the number, only for the n is equal to 0 state of the Fox state space, whereas coherent state, regardless of how strong alpha is, it is always a minimum uncertainty state. That is the beauty of it. Now, and this has interesting consequences. Okay, now people don't want to stop at minimum uncertainty. Now, there is, when you are going to, like, at the beginning of the lecture, we talked about quantum metrology. Metrology is the science of measurement. So you want to look at, you want to be able to reach a level of making measurements by beating the uncertainty principle and going to higher and higher precisions beyond the uncertainty, beyond that permitted by the uncertainty. So there are an interesting set of states known as the squeezed states. So the next thing, we talked about Fox state, we talked about coherent state. Now we will talk about the squeezed state. The squeezed states, we already have laid the we have already have written down the uncertainty relation. It makes it easy for us to write down the squeezed states. So squeezed states are a class of states in which your delta x and delta y have unequal uncertainties such that let me write down. So squeezed states are a class of states in which your delta x square is less than half or delta y square is less than half. So if delta x square is less than half, consequently your delta y square will be greater than half, such that your delta x delta y is equal to half. So here this means delta x square is greater than half, so that the uncertainty principle is not violated. Okay, so these are a class of states which are known as squeezed states, which means if you are looking at making measurements of one or the other of the quadratures in one of these squeezed states, you are going to be able to make a measurement which is more precise than permitted by the minimum uncertainty state. So these squeezed states were hugely studied in the context of gravitational wave detection, because the gravitational wave detection, the disturbance that is caused by the gravitational wave is something of a very, very small nature, that it is the ground state of the oscillator or any of these minimum uncertainty states do not have the resolution to measure those things. So you need to look for states which give you which do better than this. Okay, so with that, the squeeze states have been hugely studied starting from late 70s, and there are lot of things have been developed in this. So these squeeze states have the interesting property that the minimum uncertainty, you can beat the minimum uncertainty principle, and you can make measurements in one of the quadratures with precision higher than allowed by the minimum uncertainty principle. Of course, the other one will take the baiting here. So same thing. So this R is very important. You cannot have AND relation. You can only have a or here. So these are squeeze states for you. And all these states, what we do in quantum optics is that I think I have run out of time. I wanted to just bring in one more information as Panigrahi has requested. So after you have done, and there are many other states also, like, you have already looked at the coherent state. And once you have coherent states, you can construct interesting superpositions of these coherent states. So this coherent state, as we have already said, that we started with looking for a coherent state to describe a field which has got well-defined amplitude and phase at the classical level, which means in the appropriate limit, the coherent state will go over to a classical, will provide you with the classical description of the radiation field. So coherent state is the, with all the important quantum mechanical properties, it is nearest to the classical description that is available to you. Now, you have a coherent state, and now you have defined coherent state alpha. You can also define a coherent state minus alpha, because alpha is complex number. What does a minus sign mean in front of that? It means that minus alpha will simply be e to the power of I pi times alpha. Okay, now there are interesting combinations. You can construct linear combinations of these coherents alpha and minus alpha, put some general phase factor in front of them, minus alpha. So these states are referred to as, Schrodinger-Cat states. So these are Schrodinger-Cat states. Now, you talk about whether the state is, in the appropriate limit, whether it is going to the classical limit or whether it is doing something other than classical. So that kind of information is called as non-classicality of the state of the radiation field. So you designate a state of the radiation field to be exhibiting non-classical property when it is not behaving like a classical state in the appropriate limit. So for this purpose, there are certain measures that you bring in order to describe whether the field is classical in nature or non-classical in nature. So there are various signatures. For example, you can look at something called the second order correlation function. For example, Prashanta, can I be given a couple of extra minutes?
A couple of extra minutes here.
Yeah?
Yeah.
Okay, so, when you are looking at the radiation field and when you are looking at the basic interference experiment, Young's interference experiment or Michelson interferometer experiment, what are you looking at? You are bringing the field from two space-time points and combining them and looking at the resultant. So that result of the interference is expressed in terms of what is known as a first order correlation function. So the result of an interference experiment, is described by the first order correlation function, which I will simply write it as the electric field E plus R comma T, E minus R T plus tau. Let us say this is at a time T and this is at a time T plus tau. This is the first order correlation. This is known as the first order correlation function. Now, you can similarly have a situation where you are combining the intensity, like when you have a photodetector placed in the path of the radiation field, it will detect the intensity. So this is the output from the radiation field. You have taken it and you have placed a photodetector here, another photodetector here, and you have introduced a time delay in the path of one of the detectors. Let us call it PD1 and PD2, and after that you have combined them both in a photomultiplier tube. Now, when you look at the signal in the photomultiplier tube, if you detect a non-zero signal, that means the field from the photodetector 1 and the field which has taken the path photodetector 2 time delay, they both have some correlation between them. So this is the famous experiment of Hanbury, Brown, and Twist. So this is a schematic of Hanbury, Brown, that is single name, and quiz, they are astronomers, they were looking at, some measurement on stars, and they have come up with this idea, and they have not provided a quantum mechanical calculation, but for a basic understanding of that, you can look at the Hanbury-Brown and quiz at the classical level. And now the Hanbury-Brown quiz basically is measuring if you are detecting a non-zero signal in photomultiplier tube. That means that the intensity from photodetector 1, what is the output of a photodetector? It is the intensity. It is the energy of the field which you are measuring. So intensity and intensity are correlated. So when you write the intensities at the quantum mechanical level, you get an expression something like this. We are looking at single mode here. E plus R comma E plus R comma T1 E plus R comma T2 E minus R comma. Okay, let me write down, interchange these things. E plus R2 T2 R1 T1 R1 T1 E minus R2 T2. So this is the kind of expression that will explain the result of this, the output at the photomultiplier tube. So this is referred to as, because this one contains electric field to two orders, E minus RT, E plus RT. So that is referred to as first order correlation function. Using the same notation, using the same definition, this is a second order correlation function because it contains 4 of the electric field amplitudes. So this is E to the power of 4 kind of thing. This is E to the power of 2 kind of thing. So this is referred to as a second order correlation function. And now you can define a normalized correlation function so that the maximum value of the modulus is equal to unity. So by dividing it with the appropriate intensities. So this corresponds to intensity correlation, which is the second order correlation function. And this, the normalized form of this is referred to as the normalized form of the second order function is referred to as G2. And here this involves a time T1 and a time T2. So for statistically stationary fields, it is found that this function depends not on the initial time, but it depends on the time difference only. So the time difference, if you call it as tau, it depends only on G2 of tau. So tau is T2 minus T1. So this G2 tau, this is normalized correlation function. So this G2 tau is less than or equal to 1. That is the maximum value it will have. Now you can define something called the equal time correlation. That means without any time delay you have done that. That will correspond to G tau is being replaced by 0. So there are certain inequalities at the classical level which the fields need to satisfy, which are known as the classical inequalities for the fields in terms of the second order correlation function are given by this. So these are G2 tau is always less than G2 0. Okay, so this G2 0, what does it mean? When you look at this expression, when you look at this experiment, at the quantum mechanical level, what is coming out of photodetector 1 are photons. What is coming out of photodetector 2 are photons. So this photon and this photon are adding up here with certain time delay. Without any time delay, we are calling it as G2 0 in the normalized notation. So G2 tau is less than G2 0. This is the classical inequality, which means the photons prefer to come together without any time delay than with time delay. So together coming without any time delay is referred to as, photon bunching and preference. Whereas, so this is a classical inequality, and there are certain fields which violate this classical inequality. So violation of this inequality is signature. Violation of this relation is a signature that the field is non-classical. Signature of non-classicality. So there are fields which do indeed do that, which means violation corresponds to G2 tau is greater than G2 0, which means the photons are preferring to come to the photomultiplier tube with a time gap rather than together. So this is referred to as photon anti-bunching. Okay, so this is a non-classical signature, and fields which exhibit photon anti-bunching are said to be non-classical in nature. There are certain other measures of non-classicality also, which is, in terms of the second order correlation only, you write what is known as a Mendel Q parameter. So for a single mode radiation field, this Mendel Q parameter becomes A dagger square, A square expectation value minus A dagger A square divided by A dagger A. So this is referred to as Mendel parameter. So this Mendel parameter is also another measure of non-classicality. If this QM is equal to 0, then the field is said to be classical, and negative QM is a signature of non-classicality. So these are certain measures. There are many other measures also, but in the given time, I'm just mentioning these things. So I will send you a detailed notes for all the points which I tried to sort of mention in today's lecture. And I'm sorry I have taken a few minutes extra. So pardon me for that. And that would be that. I think I would now close it here, because if I want to do something more, I need 1 more hour. Okay, Prashant?
We will give you 1 more hour later. But I must say, very transparent, very beautiful. Few questions, and as Madam said, she would send her notes. We'll probably have 1 more talk from her little later. So only things which are, how is this photon bunching, anti-bunching connected? Yeah, you can open up and ask a few questions only. Please ask.
Okay, so to answer your question, even if I'm not able to see your chat box, there are ways of measuring this second order correlation function, and this correlation function, which we have written down this E minus T, like let me write E minus E plus. I think I might have written it E minus E plus. It should be the other way around, E minus E plus. E plus is the, okay, I'm sorry. So this in the excitement, this should be E minus, and this should be E minus, this should be E plus, and this should be E plus, because when I wrote down the other part, I wrote it correctly only, but here this E plus is the positive frequency part and E minus is the negative frequency part. So E plus corresponds to positive frequency, corresponds to annihilation operator A, negative frequency corresponds to creation operator A dagger. Now this in the second order, the definition G2 tau is given as A dagger T, A dagger T plus tau, A T plus tau, A T divided by A dagger T, A T, A dagger T plus tau, A T plus tau. This is the definition of the second order normalized degree of second order coherence. So this is known as normalized degree of second order coherence. Now, when you do not have any time delay, that means you are making coincidence measurements. That means the light from detector 1 and detector 2 is arriving without any time delay between one of them at the on the screen on which you are collecting the information. So that corresponds to G2 0. So there are ways of measuring this quantity G2 0 and G2 tau also. And there are certain states of the radiation field in which, like for example, the resonance fluorescence from a 2-level atom is found to exhibit this photon anti-bunching. That means the state of the radiation field that describes this resonance fluorescence from a 2-level atom is in a non-classical state, which is verified by the signature that by looking at the photon correlations, you find that there are excess correlations when there is time delay, and the correlations are lowered when there is no time delay. So excess correlation with time delay means the photons are preferring to come at individual times rather than simultaneously. So that is known as photon anti-bunching, whereas the preference of the photons to come all at once and not without any time delay is referred to as photon bunching. So this is maybe this answers part of the question. I don't know, Prashanta.
Yeah, it does. In fact, I must say, it's actually very nice. In fact, many of my things are also getting clear. Somebody asked about Wigner function. You will soon be hearing from Professor Subhash Chaturvedi about Wigner function. More non-classical aspect, Professor Upamandari Ghosh will be talking after 1 hour. So have patience. So Madam will be talking one more time a little later. So we will stop it here.
Anyway, Prashanta, I will interrupt you. If somebody asked a question on Wigner function, you know what? I was telling you that there are various measures of finding out whether the field is classical in nature or not. So there is the second order correlation function, which is one possibility, and this Mendel Q parameter is basically derived from the second order correlation function only if you look at the expression. Now there is something else. There are known as quasi probability distribution functions in quantum optics. Why do you call it quasi probability distribution function? Because in some ways it is playing the role of a classical probability distribution functions, and in some ways it is not. So those ways in which it is not playing the role of a classical probability distribution function is referred, such functions are referred to as quasi probability distribution functions. And into this class come the P function, which is due to Glauber and Sudarshan, and the Q function, and then which was proposed by somebody called Bushimi, and then there is this Wigner distribution function. So these functions play, they behave like a classical probability distribution function. You know what is a probability distribution function? When you are measuring a random variable, you can only talk about its average values, and that is a weighted average, and that weighting function is known as the classical probability function. And whenever you are talking about classical probability function, you have certain notions about it. It should be finite, it should be non-negative, it should be non-singular, and all these things. Whereas all these rules are broken by these probability distribution function in the context of the radiation fields. That is the reason they are called as quasi-probability distribution functions. Wigner function is one of them, and a Wigner function becomes negative in certain regions of the phase space, because of which by studying the Wigner function for a given radiation field, you can find out whether radiation field is classical or not. Similarly, P function also. P function can become highly singular, it can be non-existent, and it can just blow up and things like that. It can become negative. So all these things are signatures of non-classicality. So study of these distribution functions also will give us information about whether the field is exhibiting classical nature or not. The or not, we could have said quantum mechanical, but people want to play it safe, so they call it non-classicality. That is the answer. That I think is the answer for the question which Prasanta was about to ask. And as he said, Professor Chaturvedi is going to talk to you about all these things. And Prashanta, okay, with that I'll take my leave, and thank you for the extra time.
Thank you so much. Honestly, it's a very, very transparent, very nice talk, and we are waiting for your notes also. Thank you so much.
I will do that in my own time, Prashanta.
Sure, no problem.
Okay, and I will send it to the QIQT group so that you can distribute it to the others. Okay?
Yeah, thank you.
Right. Thank you for the